In this last video of 3.6, we're going to be talking about some important theorems about the row and column space. The first of these is Theorem 3.6.6, which relates back to the idea of solving a linear system of the form ax equals b. Remember, such a system will have three possibilities. One, it may have no solution. Just there's no x that actually satisfies that equation. It may have a unique solution, or it may have infinitely many solutions. There's actually no in between here. If it has any solutions at all, there's either exactly one or there's infinitely many. Now, Theorem 3.6.3 actually has two parts. The first part says that if ax equals b is consistent for any b, so this applies for every b in Rn, this is consistent for every b if and only if the column vectors of A span all of Rm. To rephrase this, that means that if the column space is all of A is all of Rm, then no matter what vector b we pick from Rn, we always have a solution. That means we are always in possibilities 2 and 3. The second part says that if ax equals b has at most one solution for every b in Rn, again, we're talking about covering every single b, it has at most one solution for every b if and only if the column vectors of A are linear independent. Again, rephrasing this, that means that if the column vectors of A actually are a basis for the column space, that we don't have to get rid of any vectors like we did in some of our examples, then we always must be in possibilities 1 and 2. We cannot have infinitely many solutions. That means that the dimension of the column space has to be the same as the number of columns as our matrix. This also means that if we put A into row echelon form, every column has to have a leading 1 in it. If you remember that the leading 1s correspond to basis vectors in our column space. Now, of course, if A is a square matrix, if m equals n, then we can combine both parts of theorem 3.6.3 into a corollary, 3.6.4. Basically, for ax equals b to be consistent for every b, then A has to be non-singular. But because of theorem 3.6.3, being consistent means that the columns of A both span Rn and are linear independent. And that is exactly what we need by definition to be a basis for Rn. So being non-singular is equivalent to the columns of A being a basis for Rn. Now we're going to talk about the rank of the matrix A. Remember, the rank of A is the dimension of the row space of our matrix. But we're also going to talk about this other idea. So remember, let's write it down here. Rank is the dimension of the row space. But we also have this other number that's associated with our matrix, what we call the nullity. The nullity of A is the dimension of the null space. So hopefully the names of those will kind of point you in the correct direction. Nullity obviously has to do with the null space. But even though we come up with these two numbers that are related to A, it turns out that they are not unrelated to each other. The rank plus the nullity always has to equal the second number in the size of our matrix. So here we're talking about A being m by n. So our matrix A up here is m by n. The rank of A plus the nullity of A has to equal n, not m. Of course, if A is a square matrix, if it's n by n, then we don't really have to worry about that, but otherwise we do have to be very careful about it. But let's think about why this is true, and we'll kind of use some of the details from the proof, but we'll go ahead, I'll take one of our examples, and I'll demonstrate exactly what is going on. So let's, from our third example, wait, was this? No, this was our second example, but it was problem 3. We had the matrix A, which was 1, 2, 2, 3, 1, 4. And then we have 2, 4, 5, 5, 4, 9. And then finally 3, 6, 7, 8, 5, 9. That's our matrix A. We want to discuss the rank and the nullity of this matrix. If we put this into row echelon form, and we did this in the actual example, so I'm just going to write down a result. There's going to be a lot of zeros here. 3, 0, 2, 0, and then 0, 1. We look at the columns of this matrix U. Every column, we either have a leading 1, so those are columns 1, 3, and 5, or it's a free variable. Those are the free variables correspond to columns 2, 4, and 5. Now, if we want to talk about the rank, we're talking about the dimension of the row space. But keep in mind, every basis vector for our row space, once we put it into row echelon form, is going to be a row that actually survives. It's not all zeros. And every single row that survives is going to have a leading 1. So to form a basis for our row space, we actually end up with exactly 3. We have one corresponding to this leading 1, to this leading 1, and to this leading 1. So in this particular case, what was our rank? We know our rank is equal to 3. Our nullity, on the other hand, if we talk about the null space, well, what do we do there? We realize that every free variable is another choice to make a basis vector for the null space. And so exactly what the free variables are determines how many basis vectors we're going to have for the null space. So essentially, we have a choice of x1, well, we need to determine x1 through x6. But since we're able to pick numbers for x2, x4, and x5, because those are free variables, that gives us essentially 3 degrees of freedom. That means our nullity is actually going to be dimension 3. And so what it comes down to is the number of free variables and the number of leading 1s. It obviously has to make up how many columns we have of our matrix. But the free variables turn into our nullity, and our leading 1s turn into our rank. So if we put the rank and nullity together, we have to have the same number as the number of columns of our matrix. So in retrospect, it's not that hard to see why this occurs. It's just the two different parts of our row echelon form these two distinct spaces, but they're just two, not really halves, but two equivalent parts of the same whole. But there's another consequence of exactly what we just did there. Remember when we talked about the leading ones, we from our Gaussian elimination, we just said that it's the same number as the rank of our matrix. It's the same as the dimension of the row space. But we also use those same leading ones to talk about a basis for the column space. So each of those leading ones does in fact give us a basis vector for the column space. Not exactly straight from the matrix U, but we had to take those positions of 1, 3, and 6 and take them back to the matrix A. We did that back in our example video. And because we're using those same leading ones, what does that mean? That means that the dimension of our row space and the dimension of the column space these have to be exactly the same thing. They're both the same as the number of leading ones we had in our row echelon form. But like we said, the dimension of the row space is the rank of the matrix. And back in our definitions, I said we could have talked about a row rank as the dimension of the row space and the column rank as the dimension of the column space, but we have that these two dimensions always have to be the same thing. So that's why we just refer to it by the single word rank. That's what this theorem 3.6.6 is saying. It's just a consequence of what we were just doing. That the rank has a few different interpretations. We can say it's the dimension of the row space. I mean that's our definition for it. It's the dimension of the column space. The way we just proved this, it's the number of leading ones. Or we can go back to the rank-nullity theorem and say it's the number of columns minus the nullity. So we have four different ways of thinking about what this rank number actually means for our matrix. And it's actually really surprising that the row space and the column space always have the same dimension. But that's going to have important consequences to us or for us when we start talking about what a matrix means in terms of linear operators in the next chapter. So take a look at these kind of things, work out their examples, work on the problems for this in our assignment for this section, and I'll see you guys in the next section. And then really the next chapter. We're gonna be moving on to chapter 4. So see you guys then.